Jai Hind everyone. Today we are going to discuss the heap sort algorithm. Now, by using this heap sort, we can sort the elements. Now, as we know, there are lots of sorting algorithms, and every sorting algorithm has its own features, its own pros, and its own cons. Now, when we today's objective is we are going to discuss the implementation of this heap sort, and we are going to test and we are going to analyze the performance of this heap sort algorithm. Again, we will also discuss the comparisons between heap sort algorithm and some other popular algorithms like merge sort and quick sort. Now, when we talk about this heap sort algorithm basically implements a data structure. It uses a data structure, that is, we call that data structure as heap. Now, when we talk about this heap data structure, again it is a collection of objects or collection of certain values. Now, it has basically two properties. The first one is complete binary tree. So, when we talk about this heap in the implementation, it is just operates as a binary tree, and a binary tree which is complete in nature. Now, and the second property is it maintains a heap order. Now, when we talk about the heap order, there are basically two orders. The one is min heap order and max heap order. Now, when we are talking about this heap, it is basically implemented as an array. So, we use generally an array to use or utilize or implement this heap, and now based on the elements which are stored in this array, they just behave like a tree, or we just operate certain algorithm which will responsible for the operation of this array as a heap. Now, just take an example of this tree. Now, we can see that this is a kind of complete binary tree, and now we are looking at the basic properties we are following here. So, now when we talk about this tree is implemented in the memory or stored in the memory as this array. Now, we are functioning the functional properties of these elements which are stored in an array, they are like heap. So, this is a kind of abstract data type where we are actually storing it as an array, but we are operating as an tree. Now, this tree, it looks like a complete binary tree. Now, just take a look here. If I am going to just give indices to these array elements, the 19 will be at first index, the 12 will be at second index, and 16 will be at third, and so on. And if we are creating a heap out of this array, or we are just operating on this array as a heap, in that case this 90, the element which is available at index 1, it will be root node, and the element which is available at second index, it will be the next index, the leftmost element at second position. So, we can just define these positions on the basis of the labels of the tree. So, suppose that root is available at the first label, then next two elements will be available at the second label, and next elements will be available at third level, and so on. And each level will be filled other than the last level. So, this 16, it will be at third position here. Now, this 1, it will be at fourth position, this 4, it will be at fifth position, and this 7 will be at sixth position. So, this is how we can just create a heap out of the array. Now, based on those assumptions or based on those functionalities, in this heap, we can find out parent of any particular node, left child of any particular node, and right child of any particular node with these calculations. So, suppose I am creating a tree here. And I am giving certain positions here. I am taking this node which is available at second position, and I want to find out the parent of this node, the left child of this node, and the right child of this node. And I want to find out that these parent, left or right child will be available at which index in array. So, we are using the index because physically it is stored in an array. So, let us say we are just considering this node with index 2. Now, what will be the parent of this node? What will be the index of the parent of this particular node? So, we can obtain the index of its parent by this formula, that is floor of I by 2. Now I am going to find out I by 2, that is 2 by 2. So it will be 1. So we can say that the parent of this node will be available at index 1. So that will be your parent. So we can say this is the parent of this node which is available at index 2. Now if I want to find out the left child of this I, then I can find out the left child of this I by 2 into I. So here the value of I is 2, so it will be 2 into 2, which is equals to 4. So element or the node which is available at this 4th position will be its left child. Now if I want to find out the right child, then I can use this particular formula and find out the index of its right child. So it will be 2 into 2 plus 1. So that will be your 5. So we can see here that at index 5 we will have the right child of this particular node. So these are the basic arrangement properties of a particular heap. Now when we talk about the heap order property, each heap maintains basically two properties. The first one is min heap and max heap. Now when we say min heap, in min heap each and every node, for each and every node it is true that it will keep the value higher than its children's. And in max heap, a particular node will keep the values which are higher than its children, and in min heap a particular node will keep the value which are lower than its children. So let's say we are taking two examples here. Suppose at this node we are having value 5, and here we are having 10, and here we are having, let's say, 12. And we are having another tree that is having the value 15 at its root, and we are having 10 here, and we are having 5 here. So here we can see here that for this particular node, it is keeping the value which is smaller than the values of its children. So we can see this 5 is less than 10 and 5 is less than 12, and this 10 and 12 are left and right child of this particular node. Similarly, we can see here that this particular node, root node, is having the value which is higher than the values of its children. So at every point, each node will have the higher value than its children will be known as max heap, or we can say it will follow the max heap order. And at any particular point, each node will have the value which is smaller than, or we can say equal, smaller than the values of its children. Then we call that particular heap as min heap, or we can say it is following the min heap order. So now we can formulate this max heap and min heap, that the value which is available at the parent of I will be greater than or equals to the value which is available at AI, and for min heap the value which is available at parent of I is less than or equals to the value which is available at AI. So this is an example of this max heap. So in this complete binary tree, we can see that at each level for every node we are following the max heap property. So just take a look at this root node. So this is having 19, and its left child is having 12, and its right child is having 16. So this root node is having the value which is higher than this 12 and this 16. So at this particular point it is following the max heap order. Now for this node again we can see that it is also following the max heap order, and at this point it is again following the max heap order. Now in this max heap order there is no relation in the values of the siblings. So suppose we are checking for this 19. in that case the left child is having the value 12, which is smaller than the value of its right child. The situation can be reversed. Let's say it can have 16 and it can have 12. At that point of time, it is also true and it is also maintaining the max heap property. And just take a look at the min heap here. Now, at this, in this tree, what we are having at each point of time or at each node, it is following the min heap order or min heap property. So, for 1 is having the value which is smaller than the values of its children. Similarly, we can say for this 4. Similarly, we can say for this 16. So, this is your min heap example. Now, in this lecture, we are going to use the max heap to apply our heap sort algorithm. So, although we can use max heap or we can use min heap. So, let us say every time we are going to, in each data structure, we just do certain operations. One of the popular operation is insertion. We have to insert a certain value in a particular data structure. So, how we can insert a particular value or particular new node in a existing heap. So, the first step is add a value at the lowest level. So, suppose we are having this kind of structure in this heap. So, at this level 1 we are already having a node, and at this level 2 we are having the node here. So, this is your empty position. So, we can insert this node, a new node here. Now, after that we have to maintain the max heap or min heap property. Now, it depends on whether we are using max heap or we are using min heap. If we are using max heap, then we have to restore the max heap. And how we can just restore the max heap property or min heap property? We will check the value of the newly inserted node to the value with its parent. So, if when we are just talking about the max heap, if the value which is available in the newly inserted node is greater than the value of its parent, then we will swap the values, and we will continue this comparison until we find out that max heap property is there or till the root node. Similarly, we can say for this min heap, that for the min heap, again if we are just inserting a new node, then we are going to check the value of this new node to the value of its parent, and if the value of this new node is smaller than the value of the parent, in that case we will swap the values and we will go on checking till the min heap property restores or till the root node. So, here we are just taking an example. This is your max heap. Now, we are going to insert a new node here, a new value here, 70. So, we can say that this level is filled, this level is filled, and this level is filled from left to right till this point. So, we can just insert a value at this point. Now, we can understand in the structure of array, and if we are understanding this in the structure of array, it will be more simple that we are having 19, then 12, then 16, 1, 4, 7. So, if we want to insert a new value, then we can just insert at the last index or the next index from the last index. So, this will be your last level which is to be filled. Now, at this particular point, we can see whether this subtree is following the max heap property or not. So, we can see that this subtree is not following the max heap property. The newly node is having the value 17 and the value of its parent is 16. So, 17 is higher than 16. So, what we will do? We will just swap these values. So, after swapping these values, we will check that now certainly we are changing the value here. So, again we cannot guarantee that it will violate the max heap property above or not. So, we have to check here also. So, we will check the value of this 17 with this 19 and we find out that here the max heap property is already there. So, we will stop here. So, now this is your max heap. So, every time we are inserting a particular value, we have to restore the max heap or min heap property. The second operation is deletion operation. Now in this max heap or min heap, we generally delete the value which is available at the root node. So in that case we can say we are having a delete max operation and we are having a delete min operation. Now whenever we are talking about this delete max is deals with max heap. Because only in max heap we can find out the maximum value at the root node, and delete min is followed in min heap, as minimum value among all the values which are stored in data structure will be at root node in min heap. So what we do here, now whether we are using this max heap or min heap, or whether we are just performing this delete max or delete min operation, in both the operations we just swap the values of the last node with the value which is available at the root node, and we just eliminate the last node, and at that point of time we just restore the max heap and or min heap property from the root node to the bottom. So every time we just check that part at root node whether it is maintaining the heap property, and if it is not, then we will swap that particular value with appropriate value. So this may be a structure like we are having 1 here, and we are having 4 here, and we are having 5 here, and we have to maintain the max heap property. So we will check this 1 with 4 and with this 1 with 5. So whoever is the largest among these 3 will be at root node, and this 1 will go at that value's position. So this is how we just restore or maintain the heap property. Now heap sort is a sorting algorithm that works on the basis of this heap, and it utilizes the properties of this heap. Those are max heap or min heap. So based on the properties of those heap or the heap order, we are just implementing a particular sorting algorithm, and this algorithm is known as the heap sort. So when we talk about this heap sort algorithm, there are certain procedures we follow on this heap. The first procedure is heapify. Every time we are just maintaining the heap order, whether we are just removing the element or inserting the element. The second operation, and basically it is the first operation, build heap. So every time we are going to sort a particular array, the array initially is not in the heap form. So first we have to just build the heap, and we build this heap with the help of this heapify operation. So this heapify operation is most important in this heap sort, and by using both the operations we implement this heap sort algorithm. So first take a look at this heapify operation. So we are going to discuss the algorithm here. So for that we are going to just create an example here. So every time in this heapify we are having certain input, that is A and I. A is the element which are available in our array, and I is the index. Suppose we are just having certain arbitrary numbers here, let's say 5, 3, 10, 11 and 16. So these are the values we are having in this array. The actual storage will look like this: 5, 3, 10, 11 and 16. Now the first thing is we are just passing in this heapify the array and the element, the index of the element which we want to heapify. So suppose I just want to heapify the element which is available at index 2. So our parameters will be A and 2. So the first thing is, what we are going to do, first thing we are going to find out the left child of this I. So the left child of this I will be the node which is having index 4, and then we are going to find out the right child of this I, and which will be 5. Now here first we are just checking whether this L is less than or equals to heap size or not. That means we are just making a confirmation whether we are having the left child or not, or whether we are having a right child or not. So if L is less than or equals to the heap size of A, heap size will be the elements which are available in this heap. So for this heap, the heap size will be 5. So this 4 is less than or equals to 5, and AL is greater than AI. So definitely this 11 is greater than 3. So for that, what we will do, we will set a variable that is largest to L. So largest will point to L. Now if this condition is not true, then the largest will be I. Now we are going to make a comparison with its right child also. Now again we will check whether there is a right child is available or not. So if R is less than or equals to heap size of A and AR is greater than A largest. Now we will not make a comparison with I, we will make a comparison with largest. Then if these conditions are true, then we set largest, and finally we will check if largest is not equal to I. That means we have made certain changes. The heap order was not there and the largest value was not I. So in that case we will swap the AI with the A largest, and again recursively we will call this heapify with A and the largest, the index which is with which we have just swapped the current value. So this is your heapify operation. Now there is another operation, that is build heap operation. Now in build heap operation, we just use heapify, or we just call this heapify procedure for each and every element which is having the index from length of A by 2 down to 1. So if you are taking this example here, now here what we are having 5 elements. So length of A by 2, the length of A will be 5. So we will have A by 2 as 2. So 5 by 2, the floor value of that will be 2. So we will start from this value, and from this value down to 1 we will apply heapify operation. So each time we will just heapify each and every element, and we will do it recursively in heapify until we will make this complete array structure as heap, whether it is max heap or min heap. For current situation we are using the max heap. Now the heap sort algorithm. So in the heap sort algorithm, first we build a heap, either it is max heap or min heap, and after that for each and every element from length of A down to 2, that means from the last, we are just pointing at the first we are pointing at the last index and we are just moving towards the top. So for that, each and every time we will swap the element which is available at A1. So at A1 the value will be the maximum in max heap. So that value will be swapped with AI. So currently in our heap, the AI will be the last element, and after that we will reduce the heap size by 1. So that means the value which we have swapped with the last element, that last element or the last index will not be the part of heap, and after that we will call heapify for index 1. So now we will just again restore the heap order from the element which is available at the root. So the very simple operation here, we are just swapping the top element, the root element, with the last element. In that case the maximum element will go to the last position, and we are reducing the heap size so that we will not be able to work on the last element, and then we will restore the heap property. So let's take an example here that we are having an array. Now first we are going to create a heap out of this array. So first we are going to picture this array as a complete binary tree. Now you can see that in complete binary tree we are just arranging the elements of the array as they are available in this array. So this 16 which is available at index 1 will be available at the root, and in the same order we will arrange all the elements in this complete binary tree. So in this binary tree what we have to do, we have to maintain the heap order, or we have to just create a, or we have to build a max heap here. So first we will check for the value which is available at the last index. So 19, we will check the 19 with its the value of its parent, and we find out that the value of its parent is smaller than the value of 19. So in that case we will swap 19 with 7. So now 7 will come at this index point and the 19 will go at the value at the place of 7. Now we will check for this 7 again, but now we are not having any child for this 7, so we can continue to the next index. So we will check for this 12. Again the value of this value of 12 is greater than the value of its parent. So we will swap 12 with 4, and again the 4 is not having any children, so we will move to this 1. At 1 we need not to do anything because 1 is already smaller than 12. So after that we will move to this index 19, the value 19, and at this particular point we will check and we find out that the 19 is greater than the value of its parent. So again we will swap the value of 19 with 16. So in this order we will swap the 19 with 16, and at this particular point we will check again whether the value of the 16 is smaller or greater than this 7. Now if it is greater than its children, then it is okay, it is already a max heap. So, and if it is not, then we will again apply the heapify operation recursively. Now in this heap sort, till now we have created a max heap. Now we can apply a heap sort algorithm to sort the elements in which are available in this max heap. So first we have, if we are going to just sort these elements in decreasing order, we generally use min heap, and if we want to sort these elements in increasing order, we generally use max heap. So in this again we will just take out the maximum element or the element which is available at the root, and we will move the value which is available at the last level to the root. So this 19, we will separate this 19 and we will just move out the value of this 7 to the root. So in other terms we can also say here that we are swapping this 19 with 7, and at that point we are just reducing the size of the array. So that happens in the actual algorithmic implementation. After taking out this 19, we will have this 7 here, and we have to maintain the max heap property for this 7. So we will swap this 7 with 16. So after swapping with this 16 with 7, again we will take out this 16 and we will move the value of this 4 to the root node. So now we are having the sorted elements 19 and then 16. After that again we will follow the same procedure. We will check whether this 4 is holding the property of max heap or not. So we find out this 12 is greater than this 4, so we will swap this 4 with 12, and after that we will find out, we will check whether this 4 is having the max heap property. So here this 4 is containing the max heap property. Now we will again take out the biggest, that is 12, and we will move the element which is available at the lowest level to the root node. So again we will check whether it is maintaining the max heap property or not, and we will swap this 1 with 7. After that we will take out the 7, and the 7 will be the part of this the sorted sub array. Actually they both are the same arrays, the working is in same arrays, and then we will move the 1 to root node, and after that we will heapify. So after heapify we will have 4 at the top, and we will just take out this 4, and now we are only having one element, and we just take out that element also. So in this way we can sort a particular array using heap sort algorithm. So this is your sorted array. Now when we talk about the time analysis, there are certain procedures we are having. The first one is build heap algorithm, then we are having heapify operation. So build heap algorithm, it runs in big O of n times. So because we are just calling this, we are just running this build heap algorithm, and we are having a loop in this build heap algorithm, and that loop will run for each and every element which is available in this heap. So it will run for order of n times, and each time we are calling this heapify operation, and heapify operation will have at max order of log n recursive calls. So by combining both the complexities, the heap sort will run in order of n log n time. So the time complexity of this heap sort will be order of n log n. Now there are two more sorting algorithms which are having the same complexity, that is order of n log n. Those are merge sorts and quick sort. Now when we talk about the quick sort sometimes perform better than the heap sort, but in general when we talk about each and every case of quick sort, the worst case of quick sort is order of n square, but the worst case of heap sort, or the worst case, best case and average case, all the three cases are having the order of n log n time complexity for heap sort. And again in case of quick sort algorithm, there is an extra storage we are using, and that will take a log n amount of extra space. So the space complexity for this quick sort is log n, but heap sort is not having any space complexity, or we can say the heap sort is having the space complexity as order of 1, as it is a in place sorting algorithm. So in that sense heap sort is better than quick sort. And when we talk about the comparisons with quick sort, heap sort and merge sort, again merge sort is also having the auxiliary space required as omega of n. So we require a certain n amount of space, n amount of extra space to implement this merge sort, but in heap sort we are having the constant time complexity. So in those terms heap sort is better than merge sort. Now when we talk about the storage complexity, how it plays a role. So when we talk about certain applications where we are having the restricted amount of storage, like the embedded systems or smaller devices, in that the storage is limited. So in those devices the heap sort plays a very vital role. And when we talk about the devices which are having the larger memory, in those cases we can just omit the requirement of space and we can switch to other faster sorting algorithms. So the possible applications for this heap sort algorithms are, generally they are used in scheduling algorithms. So whenever we are whenever we want to just schedule something, we use heap sort. As in max heap also works as a priority queue, and every time we are just picking a particular value by using heap sort which is having the maximum priority, or we can say the maximum value. So in schedulings the use of heap sorts can also be there. So the conclusion of this lecture is, we were discussing the heap sort algorithm, and the primary advantage of this heap sort algorithm is its efficiency. Now when we talk about the time efficiency or the memory efficiency, the time of efficiency, it is having the complexity order of n log n, and the space of memory efficiency, it requires the space complexity for this is constant, that is order of 1. And heap sort, it is having basically two major steps. The first one is building max heap, the second one is heapify. So that's it for this lecture. Thank you.